Welcome to A-Level and EP Physics. In today's lesson, we will discuss past paper questions on astronomy and nuclear physics from October-November 2022, paper 4, variant 1. In the last videos, we have discussed questions from question number 1 to question 8. And today's lesson, we will focus on question number 9 and question number 10. And for the solution of first 8 questions, you can go to the channel and you can search for October-November 2022, paper 4, variant 1. And you will find a detailed solution of first 8 questions, and understanding of those questions is very important because those questions are based on new syllabus. And in today's lesson, as always we do, we will discuss these questions in detail so you can improve your conceptual understanding of these topics, and also you can have better understanding of these questions. Let's study together, let's improve together. For question number 9, part A, we need to state what is meant by the luminosity of a star. And luminosity of a star is the total amount of energy radiated by a star per second. Or simply we can say luminosity is equal to power of radiation, total power of radiations. So this is what we call is luminosity of a star, power of radiations. Now in this case, if you look at this figure, so here we have a beautiful star. So the luminosity of the star means that total amount of energy radiated by this star per second. So that one is the luminosity. So simply we can say for the luminosity is the total power of radiations emitted by the star. And this question is a typical question. It's possible if there is any question about astronomy in your final exam, you will see this in your exam. I mean, they will ask you to state what is luminosity of a star. So you have to be very clear what is luminosity of a star. And let's move on to part B. For part B, it is given to us a star in the constellation Canis Major is a distance of 8.14 times 10 to 16 meters from the Earth and has a luminosity of this one. The surface temperature of the star is given. Calculate the radiant flux intensity of the radiation from the star observed from the Earth. Give a unit with your answer. So question is simply asking us about intensity. Radiant flux intensity. It simply means that this is the intensity. And in this case, we need to write down what is intensity. Intensity simply is equal to F, and F is equal to L divided by 4 pi d square. And we have the value of luminosity. So this is value of luminosity. Luminosity is equal to 9.86 times 10 to 27. And this is divided by 4 pi d square. D is the distance. So we have here distance is given. That is 8.14 times 10 to 16 square. And now if we solve this one, we can find out value of radiant flux intensity. But question is also asking us to write down the unit. So the unit of luminosity is watt and unit of distance is meter square. So the unit of this one will be watt per meter square. So this is the unit. Now before we write on the final answer, let me explain you the difference between radiant flux intensity and the luminosity. Radiant flux intensity and luminosity. Let's try to understand the difference between these two with the help of this figure. So luminosity is the total power radiated by the star per second, and intensity at any distance. For example, at this point we can calculate value of the intensity. This is the amount of energy per second reaching this unit area. That one is the intensity, means power per unit area. So reaching at this point, that is intensity. And intensity we need to understand, it depends on distance. So the intensity of the star at this point, let's say this is point A and this is point B. Intensity at point A and intensity at point B will be different because intensity depends on distance from the star. But luminosity is intrinsic property of a star and it does not depend on distance. So you have to be very clear about this point. Let's try to understand a little bit more about intensity. Why intensity decreases with distance? The reason is that amount of energy produced by the star per second is constant. I mean, luminosity of a star is the intrinsic property of a star. So we are assuming that is constant. That intensity depends on the distance. So it simply means that the same amount of energy is spreading over larger and larger area. So as energy spreading over larger and larger area, so it means that energy per unit area will decrease. So that's reason intensity decreases. So first of all, you can imagine that energy is concentrated at single point, then energy is concentrated at this much area, then at this much area, then at this much area, then energy is spread it over this area, then this big area, then that big, very large area. So it means intensity will decrease, energy per unit area is decreasing because same amount of energy is spreading over larger and larger area. So you must have this sense. Now simply just remember the formula. Radiant flux intensity is luminosity over 4 pi d squared. So you must have sense about this one. So you can get feelings about physics. So you can understand these quantities. Now let's try to write down our final answer. And so simply if you use calculator and you calculate these values, the final answer should be equal to 1.18 times 10 to minus 7. So this is intensity, 1.18 times 10 to minus 7. Now the question is that why we're using 3SF? Because in the given data you can see this one has 3SF, least number of SF. This one also has 3SF. So least number of SF in the given data is 3SF. So in the final answer we are also using 3SF. So if you do this one, you will get 2 marks. For the second part, we need to determine the radius of the star. So we have temperature of the star, surface temperature of the star, and we have luminosity of the star. We can use these two quantities and we can determine the radius of the star. So you can see how beautiful physics is. Our physics make our life easier. So we are just sitting on our planet, we have the luminosity, we have surface temperature, we have determined using other methods, and now we can find the size of the star. So for this purpose, simply we have to use Stephen-Boltzmann law. According to Stephen-Boltzmann law, luminosity is equal to 4 pi sigma, this is Boltzmann constant, times r squared, this is radius of the star, times T to the power of 4. And this is thermodynamic temperature, means temperature has to be in kelvins. Now simply we need to find out value of R. We can plug in values and we can find out value of R. Otherwise you can also rearrange this one. We can write down in this case R squared, this will be equal to luminosity, divided by 4 pi. We have sigma and here we have T to the power of 4. So we need to find out radius in this case. We need to find out radius, so we can take square root on both sides. Square root means the power of this one is 1 by 2. And now simply we need to plug in values. The value of luminosity we have, that is equal to 9.86 times 10 to 27. This value we have, this was given to us in the last part, and we have 4 pi, so here is 4 pi, and we have value of Planck's constant, that is equal to this is Stephen-Boltzmann constant, not Planck's constant. So this is Stephen-Boltzmann constant, its value is 5.67 times 10 to minus 8. Then we have temperature that was given to us in kelvins, 9830 to the power of 4, and then we need to take square root of this one, 1 by 2. If we solve this one, our final answer will be equal to 1.22 times 10 to 9 meters. So this is the radius of the star, and this is how we can calculate. So simply we can say this is 1.22 times 10 to 9. And this question has 2 marks. If you have written Stephen-Boltzmann law, you will get 1 mark C1, and if you got the right answer, you will get answer mark means A1. And again, we are using 3SF here, because in the given data, least number of SF is equal to 3SF. So we have to use 3SF in the final answer. Part C says, explain how the surface temperature of a distant star may be determined from the wavelength spectrum of the light from the star. So wavelength spectrum simply means that you can see here, this one is the wavelength spectrum. We have wavelength on x-axis and we have the flux, means the intensity, on y-axis. So if this spectrum of a star we have, so how we can determine the surface temperature of that star? For that purpose, we need to understand Wien's displacement law. Wien's displacement law. Let's say if we look at this star here, so we can find out its peak wavelength. We can find out lambda peak. So we can say lambda peak, according to Wien's displacement law, lambda peak times surface temperature in kelvins. This surface temperature has to be in Kelvin. This is equal to constant. So this one is equal to constant. It simply means that this is true for any star. So simply we can say then lambda peak, I will say lambda 1 times T1 for one object if we have. So then for the second object, let's say this is lambda 2, and and we need to find out T2. If we have lambda 1 peak wavelength of one star, and we have its surface temperature in kelvins, and we have its wavelength, and we need to find out surface temperature of the second star. And so in this case, simply surface temperature of the second star will be equal to lambda 1 T1 divided by lambda 2. So we can find out surface temperature of another star. If we have lambda peak and thermodynamic temperature means surface temperature in Kelvin, and we have the wavelength spectrum of a star, so we can determine the wavelength of that star. So this is simply how you can use Wien's displacement law. If you have the wavelength spectrum, I mean if you have this spectrum, from the spectrum first of all you will find value of lambda peak. When you have value of lambda peak, then you can look for another object, or you can look for another star which has known value of lambda peak and known value of surface temperature, and then you can use Wien's displacement law and you can find out value of surface temperature of unknown star. So this is how we use Wien's displacement law. So how to write down the answer? So let me show you the answer, how you can write down the answer. So in this case, you can write down wavelength of peak intensity determined from the spectrum of the star. So this is step 1. So step 1, when the wavelength spectrum is given to you, you can determine the peak wavelength. So we can say this is step 1. You can determine this one from the given wavelength spectrum. And wavelength of peak intensity from object of known temperature determined. So if you have another star, for example, so just imagine that we have this red one. We have value of its peak wavelength, and also we have its surface temperature. We have its surface temperature. Then what we need to do is simply we need to use this ratio, means Wien's displacement law, and we can find value of surface temperature. So you can say using Wien's displacement law, we can determine surface temperature of a distant star. So these 3 points you have to write down. If you write down these 3 points, you will get 3 marks. And these are B marks. Question 10 says carbon 15 is an isotope of carbon that undergoes radioactive decay to nitrogen 15, which is a stable isotope of nitrogen. Radioactive decay is both a random and a spontaneous process. State what is meant by random and what is meant by spontaneous. These 2 terms are very important for your exam, so you need to understand how to state these 2 terms in a proper way. First of all, let's try to understand what is random. For random, we can imagine that we have a sample, and this sample, imagine that it consists of 4 atoms, or simply you can say 4 nuclei. So this sample consists of 4 and 4 nuclei. Means it consists of total 8 nuclei. And random means that we understand after one half-life, half of them they will decay into an other element. But we cannot predict in this case when this one particular nucleus will decay. So that is random. Means it cannot be predicted when a particular nucleus will decay. So it cannot be predicted. So this is what is meant by random. Now let's try to understand spontaneous. Spontaneous means that radioactive decay is independent of temperature, is independent of pressure, and also independent of neighboring nuclei. So when the time will come, it will just decay. Means radioactive decay will happen. But we cannot accelerate this one by increasing surrounding temperature, or by increasing pressure, or by neighboring nuclei. So this is what is meant by spontaneous. I hope this is clear to you. Let's try to write down the answers. In your answer, you can mention these points. In your answer, you can write down cannot predict when a particular nucleus will decay. You can also say for spontaneous, it is not affected by external factors such as temperature, pressure, or neighboring nuclei. So if you write down these 2 points, you will get 2 marks. Part B says a small sample of carbon 15 decays. The mass capital M of carbon 15 in the sample decreases with time t. Figure 10.1 shows the variation with time t of the value of ln m. For part B1, we need to state how figure 10.1 demonstrates that radioactive decay is random. If you look at this figure, and this line you can see is fluctuating. There are fluctuations in this line. It means that the radioactive decay is fluctuating. So it means radioactive decay is random. And we can see this one from the line because the line is fluctuating. So simply you can say as line fluctuates, it means this decay means the radioactive decay is random process. For the second part on figure 10.1, we need to draw a straight line of best fit. So simply you need to draw a straight line of best fit. So let me show you how you can draw. So this is how you can draw best fit line. This has to fit this zigzag line. So the same number of points above, same number of points below. So this is how you can draw the best fit line. For third part, we need to show that decay constant of carbon 15 is given by the magnitude of the gradient of line in P2. And this is the line we have sketched in P2. Now we need to show that magnitude of the gradient of this line is equal to decay constant. And if we look at y-axis, we have ln m on y-axis and we have time on x-axis. In order to answer this question, simply we can start with nuclear decay equation. N is equal to n naught e to the power of minus lambda t, and this is exponential decay equation. Same type of equation we also use in discharging of capacitor, because discharging of capacitor and nuclear decay, they follow exponential decay. So we can use the same equation but with different quantities for capacitor, and also we can use for radioactive decay. And this equation is also given in the formula list. But here we have mass. How mass is linked with number of nuclei. Number of nuclei and mass, they are proportional to each other. If we have more number of nuclei, it means mass will be greater. So simply we can replace n with m. So we have m is equal to m naught e to the power of minus lambda t. Now simply we need to take natural log on both sides. So ln m, this will be equal to ln m naught minus lambda t. Now, if we rearrange this one, we can say ln m, this will be equal to minus lambda t plus we have ln m naught. If we compare this one with straight line equation, y is equal to mx plus c, in this case, we can simply say gradient is equal to minus lambda, negative lambda. So we can say gradient is equal to minus lambda. But question is asking us to find out magnitude of gradient. We need to show that magnitude of gradient means we don't need to worry about the sign. Magnitude of gradient, simply this is equal to lambda, and lambda is the decay constant. This is what we need to show, means magnitude of the gradient is equal to decay constant. And this question has only 1 mark. So simply you need to understand how to write down radioactive decay equation in linear form. And this question is very popular in 2022 and also in 2023. So you have to be very clear how to write down radioactive decay equation in linear form. So get familiar with this. For part 4, we need to use over line in E2 to determine lambda, and also need to give a unit with our answer. In the last part, we have discussed that gradient is equal to negative lambda. Now we need to determine the value of lambda. So we can write down lambda is equal to negative of gradient. So in this case, we can say lambda, this is equal to negative. We can take this out and we can write down the gradient here. So in this case, I'll be taking these 2 points, 1 point here and 1 point here. You can take any 2 points on the line you have drawn. So I'll be taking these 2 points. So for this one, we'll write down delta y by delta x. So this is our value of delta y, and this is also value of delta y. And this is negative 4.8. We have value of t, that is 0, and we have value of t that is equal to 11.6. So simply we can say in this case minus 8 minus into minus, be careful with these negative signs, 4.8 divided by 11.6 minus 0. Now if we solve this one, our answer up to 2SF, it will be equal to 0.28 per second. Rate of decay constant is per second. So this is per second. So our final answer up to 2SF is 0.28. So this is how you can calculate gradient. But you have to be careful with negative signs. If you don't use this negative sign here, you will get negative answer. But lambda cannot be negative. For part 5, we need to use our answer from B4 to calculate the half-life of carbon 15. So we have already determined value of decay constant. So simply we can say in this case half-life, this will be equal to ln 2 divided by decay constant. Ln 2 is equal to 0.693 divided by, you can use calculator, you will get this number, divided by decay constant. Decay constant is equal to 0.28. Now if we solve this one, our final answer up to SF will be equal to 2.5 seconds. So this is our final answer. If you got right answer, you will get 1 mark. And this mark is only for answer. Part C says the equation for the decay of carbon-15 can be written as. Stephen explains how the mass of the products of the decay must compare with the mass of the carbon-15 nucleus. So this is our reactants and these are our products. We need to compare the mass of the products with mass of reactants. So in this case, simply we need to understand is that if this reaction is energetically possible, this is energetically possible. So in this case, energy will be released. So simply we can say energy released. If energy is released, it means mass is decreasing. As energy is released, it means it is decreasing mass. So the mass of the product, daughter products, will be lower than the parent nucleus. Mass decreases, we can say. So we say mass decreases. Because decreasing mass has been converted into energy released in this nuclear reaction. Then energy released we can also calculate with the help of this one. Delta E is equal to delta mc square, and this is the mass defect means a decrease in mass. So the mass of daughter products has to be lower than the mass of parent nucleus. So that's all what you need to understand. So let me show you the answer, how you can write on the answer. In your answer, you can mention these points. This question has 2 marks. 1 for reaction to occur, energy is released. Any reaction which is energetically possible, energy must be released. Otherwise, energy has to be absorbed. And so this is energetically possible, so it means energy is released. Energy release comes from decreasing mass. So total mass of products must be less than mass of carbon-15, means the mass of parent nucleus. And this is end of this paper, end of this question, and also end of this paper. I hope you have better understanding of these topics and also you have better understanding of this paper. I'll see you next video.